4. Shifting probability.
Problem number 4. Shooting rubber band. That's it. The reporter accepted the challenge of problem number 4. So now the preparation of the reporter, 5 minutes, and each team please write down the representative for this stage2. Reporter, please write down the name. Reviewer, write down the name. now the presentation of the reporter.
High school, and I'm going to report shooting rubber band. So entering the problem statement. Problem for shooting rubber band. Rubber band may fly a longer distance if it is not uniformly stretched, which will give it a spin. And so the problem tells us to optimize the distance that a rubber band will spin can reach. So our equipment will be the most commonly seen 18 size rubber band and a 7.5 meter measuring grid, a hanging field for the force, and a handgun with base. It has the stretch of the handgun will be 24.7 centimeters, and the muzzle height of the handgun will be 14.2 centimeters. So this is our setup of the handgun. So the stretch means from the bore to the muzzle will be 24.7, and the height of the muzzle is from the muzzle to the ground. This will be 14.2 centimeters. So our rubber band, we use the same for the whole experiment, so there will be less error from different rubber band. And for the 18 size rubber band, it has a diameter of 4.5 centimeters. But our rubber band is a little bit stretched, so it has a perimeter of about 15 centimeters. So we did 15 marks equally on it, so it was separated into 15 equal sections. So this is our layout. This one is what our layout looks from the launching side, and this one will be the one from the landing side. So our structure of the layout is not so stable, so we will optimize it with some weight. It will cause it to have less lifting and less vary from the base and the gun. And so with the weight, we also can make sure that the gun will be vertical to the ground. So our launch we will stretch the rubber band in different sides unequally, like the marks when we did earlier here. Like this one, we make different rates of the stretch. Like one part will be one to one, like 7.5 centimeters to 7.5 centimeters, and some will be 9 centimeters to 6 centimeters. And we will measure the traveling distance with the measuring tape earlier. So here are some questions that we would like to discuss. Will the rubber band act like a spring, which the force applies to F equals to Kx? And what rate of the stretch will make the longest traveling distance that the problem has asked? And also the muzzle velocity related to the rate of the stretch, which could influence the traveling distance. And also what truly makes the rubber band travel further? So our theory is a spin for the rubber band could make the traveling perhaps more stable, so causing it to travel more. And also the non-uniformly stretch consumes some of the energy for the spin. Perhaps there could be a result that there will be a less muzzle velocity. And the air resistance could also be a difference from the flight. So we stretch the rubber band in different distance. This will be a chart. So the orange line will be stretching the rubber band equally, which is 7.5 centimeters to 7.5 centimeters. The green line will be stretching the rubber band unequally. It is 8 centimeters versus 7 centimeters. So we can see that stretching a little at first, and at the rubber band stretch limit, requires more additional force for the stretch. And unequally stretched the rubber band could require less force. So here is our traveling distance to the rate of the stretch. Because the data is not really very close, so we did it many times. And also it's measured in centimeters. Here is the rate to the stretch rate to the distance of the line. So we can see that the larger the ununiformly stretched rate, the longer it would travel, and it is a lot longer. So we also try to measure the muzzle velocity with a 240 frames per second camera. So we can see that stretching it equally will be a higher muzzle velocity, but the more it's stretched unequally, the less the muzzle velocity will be. So from our launcher, we can see that the bore is a little bit higher than the muzzle. So perhaps there will be a front flip, so which could cause an effect of the air resistance. So the flip will result in a higher reference area for the air resistance. It is directly related to the object's reference area. And also there will be another force to drag it down. It will be the gravity. Conclusion will be the rubber band does not act like a spring from the previous measurement, and a spinning rubber band will resist the flip like a rotating top. So it will become a precision, not flipping. So it will not increase the reference areas. So since it's not flipping, there will be less reference area compared to the non-spinning rubber band. So it could reduce the air resistance, result in a longer travel distance. And in our setup, increasing the stretch will also longer the travel distance until it's the limit. Like we did it to 5 centimeters to 10 centimeters, and it's at the limit of the road. Okay, thank you, that's all.
Thank you. Now the questions of the opponent. The opponent asks the question of the reporter.
How do you define the unfolding stretch in the problem statement?
So we think it's
how long you stretch. Is that how you define the unfolding stretch?
yes, it's like some part.
Okay. Next question. The quick question. What's the main physics concept in the theory? Like only the Hooke's laws, your force.
Yes, and the first one.
Okay. So you don't think, yes or no question, you don't think that there is a conservation of the angular momentum?
Yes.
You think that there is a conservation of the angular momentum? Okay. How do you shoot the rubber band? Like, you let it spin like this or spin like this?
So it's stretched in the horizontal way. So
Okay,
spin
okay.
from horizontal.
What kind of app do you try to check the points on the rubber band, or you just to see how long it flies?
It's too hard to measure, so it's the
You only measure the distance.
Yes.
Okay. Does any formula in your experiments
You mean
to decide your variable?
which variable you mean?
Did you have the formula or equation that you thought that, oh, I need to use this variable?
Oh, it's only the stretch force and the rate.
So you only think that the Hooke's laws and you change the variable how long you stretch?
Yes.
Okay, that's it.
Thank you. Now the preparation of the opponent. 3 minutes. now the opponent, Yuanzhen, takes the floor. Maximum 4 minutes, please.
Hello, I'm Angel, and I'm from the Alphas team, and I'm from the Jincheng High School. The problem I'm going to approach is problem 4, shooting rubber band. The problem states that a rubber band may fly longer distance if it's non-uniformly stretched and give it a spin. So I think the thing we need to emphasize is the spin and the connection between spinning turns or uniformly stretched with its distance, how long it's fly. This is the reporter structures. The observation video is making different stretch rates in each. The theory model is non-uniformly stretched. The setup is number 18 size rubber band and a table, something like that. The experimentation is the rate of the stretching and muzzle velocity. And the conclusion is rotating in multiple precessions. And the strong point is that they have a great measure of the distance, and the setup is very clear. And the weak point is that no video for experiments, no math physics theories. He only gave me the Hooke's law and 2 simple experiments. There's too few the parameter or another variable. Okay. So this is the point to be discussed.
Now go to the discussion
Yes.
section. The reporter.
In your experiment setup, I want to ask how the experiment no page. This one. This one. So do you use the pool to that it shoots in front of us?
You mean the
I mean that have something in front of us that is this one.
yes, of course.
How do you think that it will affect the flying motion?
No, it's just for the stretch. It's not.
It's just, I mean, it will, when you fly out, it will hit
No,
the
it won't.
pools.
No, it won't.
It won't hit the pools?
Yes, it's
Because in our experiments, it will, maybe we stretch it like this and we shoot it out. It will hit the pools and make it turn over.
So in our launcher, it's only a little bit higher from the muzzle, so
Okay, I
we believe it.
understand. So you video it horizontally, like your no, you didn't have video. So your formula is only that I want to use the board. So your formula is only the Hooke's law, which is that this one.
And we did have the stand throw.
What?
Considering it as a stand throw, but it doesn't mean.
Okay. In your experiment, you did turn right or turn left?
Yes, it did.
It did. How would you think that? What effect that happened? What kind of theory?
It's not just uniform, so it will not the flying trace will not be straight.
Okay, in my opinion, I think that is a Magnus force, a Magnus effect. Do you agree with that?
Yes, they could be.
How would you think that it happened on
Because the
making turn left or turn right?
the rubber band is spinning.
Can you draw the forces?
We believe it's because the spinning side, this different side will cause it to turn right.
Can you draw it? To show me what you mean.
You mean draw one?
Yes, just how you think Magnus effects on the rubber band.
So the rubber band is spinning, so
is spinning like this,
Yes.
and the velocity of force, the air velocity goes like this, and it's spinning like this. So the force will be like goes out. The angular velocity will go like this and spin like this. So the force will go here. So it will maybe turn left. Do you agree with that?
Yes.
Okay.
But
So
we like to say the problem asks for the traveling distance, not the traveling the
but it also said that it was spin.
yes.
So when it was flying, it was spin, and that it have another force to make it fly longer. I think because another basic concept I considering is the gyroscopic stability. When it spin, it will make the flying more stable. Do you agree with that?
Yes, it's like the top.
Okay. But so you think the spin is important in the experiment,
Yes.
but you didn't consider it will affect the force. The force comes from spin. You didn't consider
It's
it.
independent from where it travels.
But if today you shooting like this, and you spin like this, there will be the air come from this one. I mean this one. The forces that it push up. If you push up, it will travel longer, right? Right.
Yes, it will.
So you also didn't consider it. Maybe you can consider it in the future experiments
No,
investigation.
I mean it's spinning like this. So there could be a lift for it being not horizontal to the ground.
Okay. I mean, maybe you can shoot like this one to see it how the force affects the
Yes,
distance.
we didn't do it first.
Okay. How do you think the radius affects how long it's flying? Because you only do the how long it stretched, you didn't do another size of rubber band.
Because the different size of the rubber band cannot, like a smaller rubber band, you cannot stretch as long as the larger rubber band.
Why? What do you mean?
Because it will break another stretch limit.
Oh, stretch limit. Because in our experiment we have do it in different sizes to see how the radius affects the rubber band. Like if we stretch it in the same length, like all invisible, and a small one and a larger one. So what do you think, or what do you expect what will happen if we stretch it like this long?
I mean, it's smaller. The rubber band is smaller. You need a larger force to stretch it, so it could fly longer.
If you didn't over the limit, so what will happen if we're using a different radius?
Yes, the smaller rubber band could fly longer. But the question asked about the uniformity to it, not about the size of the rubber band.
But
So we'd like to discuss
my point is that using different size, it also will make the spin different, the turns spin different. Because in our experiments, the smaller one will spin more and make more stability. This is also what we discussed earlier. So, okay. Have you ever think about making a mark on the rubber band to see how it turns
So
in your
we
experiment?
so we did do some marks, but it's for the ununiform stretch. But it's really hard to record like this. We recorded with it's 240 frames per second, and it looks like this. It's impossible to track.
I mean, to mark is to see the flying, the motion when it's flying.
Yes, it's
Using
already
a slow motion to.
yes, it's already 240 frames, and it looks like this. So it's almost impossible to track the flight
Okay.
motion.
Like in our experiments, we do some sticker on the side.
That might influence the.
You mean the mass, right?
The rubber.
Yeah, we don't think that it might affect the mass. So we also consider the angular momentum, like this one, to try to calculate the experiment. Did you agree with that, or because you just say that you will also have the angular momentum?
Yes, causes not do so much. It's increasing the.
You didn't think that affects so much.
No, I mean, so if there's an angular speed, so it will not fit that much to affect the error resistance.
You can put the mark is like.
Yes, so if it's flying like this, it has a less reference area, but like this, the more reference area it will be. So there will be a larger error resistance.
So in your experiments, did you try to consider the 3 dimension? Because when you're flying, it will like shaking or it's unstable.
Yes, it will.
So you will consider it in 2 dimension or 3 dimension, the motion.
So yes, the distance is it will. So if this is our launcher and it could fly like this, so it's the distance of this, not just this one. It's a 3 dimension.
3 dimension also have this one. I mean, you just take
Oh yes.
X and Y.
So,
I mean, the up and down, you will like shaking.
no, I mean the height is just 41 dimensions.
What?
So the muzzle height is just 41.
Muzzle?
Yes, we didn't change the muzzle.
You mean the height when you shoot? Or
I mean the launcher's muzzle.
the launcher muzzle?
Muzzle.
Can you explain more? I don't understand.
It's like the muzzle distance to the ground.
Muzzle this. You mean when it's flying? Like this is your motion. This is the rubber band. You mean this high or
Yes.
this high?
When down.
Going down? You mean flying?
When it started on.
Start the launch. Okay. I mean, my question is that the 3D is when it's flying, it will like shaking so that it will affect the how long it fly or the stability. Because when it's spinning, it will give it the stability to let it fly stable and longer. Right. Okay. How do you expect for the Hooke's law? Do you think that axial compressive force will affect the rubber band? The compressed force. When a rubber band is stretched to some limits, you will have a force like this to break its structure. What do you think about that?
So it's harder to stretch that. It's almost tendon. So the line is like this.
Okay. When you set up, how do you think that the rubber band, the stretch of the rubber, how do you control it? Because if you stretch it, it will have the thin one. It might be the thin one. How do you control it?
You mean in the rubber band? Yes.
When you try to shoot it, you will have the one.
So-
Maybe one side will be thicker, or
Yes.
another will be
So
thin.
we have
How do you
marks
control?
on them. Yes, we have marks on them. So we will make sure that there's a mark here, and there are
The position will be more
Thank you.
Okay.
Now the opponent summarize the discussion in 1 minute.
We have discussed about the conservation of the momentum, which the reporter also agreed with, but they didn't consider that much about the spin turns and the spin, how the spin affect how long it fly. And also in his theory, he didn't talk too much about the aerodynamic lift. Also in his experiment, he didn't do that much variable or how to change how to shoot it. It also doesn't have another parameter, so I think it will be more investigation in the future. Also, I think it's really great that the setup it didn't have the pool to affect the experiment, because in our experiments there will be a pool that affect how it fly or motion the rubber band is. Thank you.
Now the reviewer asks questions to the reporter and opponents. 3 minutes.
So thank you. So I have some few questions for you. And so the first one is about the definition. How do you define the non-uniform stretch?
We stretch it different. The stretch force is different in different sides of this rubber band.
How do you define the non-uniform stretch rubber band?
Like in our experiment, we might have a pool. We also might have a. We know another shooting machine that is like this. So if we can we shoot it out, so we can move the pool in the center to that it on the stretch.
So in your discussion, in your report, you said that you use the same rubber band.
Yes.
And do you consider if the force is too big, it will have the elastic effect?
So we believe it's better to use the same rubber band than using different rubber bands it may cause a larger error than using the same rubber band.
So you think, what do you think? Do you think it is important to consider elastic?
Of course, the elastic will affect the start force.
How did you so do you agree that you have to consider the other the 3D dimension?
You mean from the vertical to
Yeah.
ground? Yes, we should have done, but in our experiment we did the horizontal.
And
Yes, I agree.
okay, I see. And how do you calculate the velocity?
So it's 240 frames per second. So we compare two frames, the distance between the rubber bands.
Do you think that it's
Like in our experiment, we use the sticker and the motion tracker to see the points and the rest of the center to calculate the velocity.
that's all? Thank you.
Thank you. Now the preparation of the reviewer. 2 minutes. Now the reviewer, Rongxuan, takes the floor. 4 minutes.
So, so I'm the reviewer of the Robert, shooting Robert, and so. We think that the key points of the problem statement is this. So for the theory part, the reporter said that the spin will stabilize the flight. And they released this using a mechanism to they measured the horizontal flying of the rubber band, and so for their conclusion is more evenly stretched will cause higher excess velocity, and more unevenly stretched will be more stable. And so for the advantages of the reporter is that they have enough data, and they did explain the data, and they have great experiments set up to measure the distance. So for some suggestions, the first is that they didn't have the node equation in their presentation, and they could use video to more further demonstrate the phenomenon, and they could consider more parameters, and they didn't measure the other axis of the rubber bands flying, and they didn't consider how the rubber band is. And for the opponent, they have great time management, and they mentioned 3D analyzing the conservation of momentum. And so for some suggestions is that they could focus more on the reporter's experiment, and they state too much things in their light of their own experiment. And so the discussion how to define the non-uniform stretch, and the reporter said the stretch force is different in the rubber band, and we agree with it. And so the other thing is that the other discussion is how do we make sure the force react. Will cause elastic effect, and the reporter said they believe it will be better to use the same rubber band, but we think that it will affect, and it is more you should measure the elastic effect because it will affect on the experiment. And the discussion is and so for some risk points we think they didn't discuss, it's that they didn't actually discuss other variables like elastic fatigue and radius of the rubber band and the speed. That's all.
Thank you. Now the concluding remarks of the reporter, 2 minutes.
So our concluding remarks will be, in our launcher, the rubber band will hit the muzzle of the gun, and in our experiment, we let the rubber band slide horizontally. Maybe we can do the experiment that slide and stay vertical in the future. And we believe that the magnet effect won't affect the motion of the rubber band because it's vertical to the direction of the travel. And the velocity didn't increase when the rubber band is spinning. So the reason why the rubber band feels longer perhaps is because of the spin and not the initial velocity of the rubber band. And perhaps we could do more variables in the future. Thank you.
Thank you. Now the questions of the jury. So, Golden, the reviewer, please stand up. Questions, Professor Nian.
Yeah, I'm surprised that your data do not have error bar because I personally believe that this is experiment is not that reproducible. So without error bar, I'm not sure whether I can trust your data. Error bar meaning that having the same condition to the experiment, what would be the result, variation of the result?
Yes, we should add it.
Okay, the same question to each of you, followed by the opponent. How much error bar you might imagine over each data source?
Like I asked you, what's the rubber band might stretch a little bit, like thickness or the thin one. So I think when you stretch it, it might cause the error bar.
Is there any comment
from
the reviewer?
Considering the number of their data is range from 200 to 300, I think that it should be like about 13 centimeters. Or if you want to make it more correct, you should use the
Okay, thank you.
standard.
Any questions from jury? Professor Wu?
I have two questions, please. So the first one is that you guys all agree with that the spin will somehow affect the result very well. But from the discussion, I cannot see how spin will change the results. In the sense that I don't know whether the higher spin, I mean the angular velocity would be better to have a longer distance, or the lower spin velocity, I mean this accelerated velocity will increase the distance. This is my first question. So my second question is that I can somehow imagine that from this experimental setup, so this kind of idea can be applied on lots of different kinds of lesson platform. So can you somehow comment on the different kind of platforms of this kind of experiment, like how do we increase the distance when we should arbitrary?
Okay, so two questions for three teams. The first question is, how does the spinning affect the distance?
Yeah.
Who wants to answer the first? How does the spinning affect the distance of the rubber band? Who wants to answer? Okay. Opponent.
First of all, the stability when you spin. Second of all, is depend on how you shoot the rubber band. If you spin like this, you have a Magnus effect that you push up. So the spin will affect the air of the velocity and make it fly further or longer.
The comments from the reporter or reviewer. How does the spinning affect the distance of the rubber band?
So
Reporter?
the spinning will cause the less, it won't like front flip or back flip. So it will result in a less surface area with a less air resistance. So the speed will not reduce that much.
Reviewer,
I think
could
it's
you
like,
give your opinion?
I think it's like just like you can, if you spin it, there's an airflow in the middle. It'll make it faster.
The professor, good question.
So
Second
that's
question.
my second question is, can you imagine how to apply your result on different kind of method? I mean, here you only consider rule band, but I somehow believe that your experiment is somehow very broad, and can you somehow explain how to apply your result on different kind of stuff? Let's say if I would like to increase the distance, then what kind of parameter is used?
Time's up.
Oh. So it's fine. So let's answer this question. How do you optimize the distance with considering other situation. Yeah. Who want to answer the first?
Maybe some
Opponent.
material whose the decay will be larger than the decay.
Use different material.
Yes.
Okay. The opinion from the reporter.
So for using the same rubber band, going to the stretch limit will of course increase the traveling distance. And if we use a different material, of course, we can also increase the stretch limit.
So for material, the opinion from the reviewer.
I think the radius of the rubber for things that's been, and so if we decrease it, then the airflow will make it faster.
Radius of the rubber band. Thank you very much. Please sit down. Now the grading for the jury. Okay, now the grading for the reporter, please. 5, 6, 4, 6, 5. 5, 4, 6. So now the grading for the opponent. 6, 7, 5, 8, 7.
6, 5,
So wait a second.
6, 7,
6, 7,
5, 6.
5, 8, 7. Confirm?
6.
Huh?
But Professor Gu Huanyu, about opponent, the score is 6, right?
Opponent.
Opponent 7.
Or 7?
7.
Okay. Okay,
And now
it's
the
about
grading for
reviewer.
the reviewer. Reviewer. 5, 6, 5, 7, 6. So wait a second. Confirm?
Okay.
Thank you very much. Thank you. So let's